Okay, lecture today we left off talking about Bragg's law, and we talked about one of the possible applications being X-ray diffraction, and also examples of this happening with light diffraction in structural coloration. Let's do an example that addresses structural coloration, or that shows us structural coloration. So we have peacock feathers have these things called structures called barbules, containing of rods of dark melanin spaced at about a quarter micrometer apart. What color will the structure appear when viewed with light incident perpendicular to the surface? How about light at 60-degree angle to the surface? Will the feathers look red at any angle? So I've gone ahead and started or worked out the problem here. So let's start with the first piece. I'm going to get rid of this work here so we can follow this easily. So when we have perpendicular incident light, first let's take a look at the structure. This is what the structure looks like. And the distance between these barbules is about 0.25 micrometers. So this distance we know. And then the first case is we have light incident that's perpendicular, and we want to know what color will the structure appear when light is incident perpendicular. If we go back a couple of slides, Bragg's law tells us the following relationship depending on the angle that the light makes. So if we have normal incidence, this angle is 90 degrees. This is the expression we're going to use. So let's take 2d sine theta equals m lambda. So we start with 2d sine theta equals m lambda. D is the spacing between the layers. So D is equal to 0.25 micrometers. Sine theta is sine of the angle of incidence, so sine of 90 degrees. We don't really know what m is, so we'll just leave that as m. Lambda is the wavelength that we're trying to figure out, which is going to help us figure out the color. So if we can figure out at what wavelength do we have constructive interference from this type of a spacing, then we can figure out what color we see. So we go ahead and plug things in, and we get that all of this 2 times 0.25 times 10 to the minus 6 gives us basically 0.5 times 10 to the minus 6, because sine of 90 degrees is just 1. And then let's go ahead and move the m over. So before we do all these conversions, oops, sorry. So what we know is m lambda is equal to 0.5 times 10 to the minus 6 meters, which is the same as 500 nanometers over m. So we have to be very careful with m meaning meter and m meaning index. This is our index, basically, m here. Well, we don't know what m needs to be, so let's go ahead and try if m can be 1, m can be 2, m can be 3. Basically, it has to be an integer value. So let's see when m equals 1, what wavelength we get. When m is equal to 1, we get 500 nanometers, which is, if we take a look at the visible light spectrum, 500 nanometers is around a blue-green color. So we label that as blue-green. Then let's say, what if m were 2? If m were 2, then the wavelength would be 250 nanometers. Well, 250 nanometers is not part of the visible spectrum, so we do not see this m equals 2 constructive interference. This is the only wavelength that's in the visible spectrum. All right, now the second part of the question is, what if we take a look at light incident at 60 degrees? So let's go ahead and add that work back here. All right, well, I had deleted that work. I was trying to paste it back, but we'll just walk through it. So when we have light at a 60-degree angle to the surface, in this case, we still have 2d sine theta equals m lambda. Then we go ahead and let's just go ahead and solve for lambda. Lambda is equal to 2d sine theta divided by m. Plug everything in. 2 times 0.25 times 10 to the minus 6 meters, sine of 60 degrees, all divided by m. I'm going to grab a calculator to calculate what we get here. And we get that this is approximately 433 nanometers divided by, so you probably get 433 times 10 to the minus 9 meters divided by our integer m. So this is equal to 433 nanometers divided by integer value m. So lambda when m equals 1 is equal to 433 nanometers, and lambda when n equals 2 is equal to half of 433. So 433 divided by 2, which is going to be about 217. So 217 nanometers, again, notice, is not part of the visible spectrum. This is part of the UV spectrum. So you wouldn't be able to see this. So again, the only possible M value where we get constructive interference that we can actually see is M equals 1. And 433 lands around here, which is a violet blue color that we see. So to answer the last part of the question, will the feathers ever look red? Meaning, will we ever see wavelengths or see constructive interference for wavelengths in this range? Well, looking at our expression for lambda, no matter what angle we look at, the maximum value that we get for sine theta is 1, which is what we got when we look at normal incidence at 90 degrees. So when theta is 90 degrees, that's the largest wavelength we're going to see. And the largest wavelength we're going to see is on the order of 400 nanometers, 433 nanometers, which is much smaller than the range of light that would show you a red color. So will the feathers look red at any angle? No, they will not look red. All right, so that should wrap up the discussion from lecture. Now let's go ahead and move on to the material that this video lecture is supposed to address, which is resolution, Rayleigh's criterion, and thin film interference. These are the three last topics you need to finish your homework number 5. So resolution is the ability to distinguish two closely spaced objects as being separate. So let's imagine that you see a car approaching. When the car is close by, you can distinguish between the individual lights of the car. Let's say the car is approaching from further away. You may not be able to distinguish between these top versus bottom lights. So the car looks like two lights. Now let's have the car approach from even further away. There's a point where the lights of the car just look like one single spot. So when two objects are very close together and far away, you can't tell that they're separate. And that is kind of our limit, our resolution limit eventually. And this diffraction sets a limit on how close two objects can be before they seem to merge together. And this resolution limit doesn't care about, let's say you're looking at the car, how good your vision is, or how good are the optics in your microscope that you're working with. When you hit the diffraction limit, it's not a limitation of the optics, but it's a resolution limitation due to geometry and due to diffraction itself. So let's talk through what that means. So suppose that you have light from two objects that enter a small opening. Each of the beams make an airy diffraction pattern. So what is this airy diffraction pattern? We talked about single slit. Now take that single slit and imagine having a tiny aperture. So let's say you have some surface, and that surface you have like a tiny aperture or a tiny hole. And if you shine light through that tiny aperture, this is what the diffraction pattern looks like. You have a bright central spot, and then you have a dark band. Then you have another bright ring or bright band, and then a dark band, etc. And Rayleigh criterion is basically, so let's say you have two different sources through which that light from those sources shine through the aperture, and they'll form two of these airy patterns right next to each other. So here is possible examples of overlapping airy patterns. So this is the limit, and this airy pattern, if I were to take a line cut through it, it's the intensity of the light can then be plotted. That basically has your central peak, and then let's try to draw this a little more carefully. So this thing hits a minimum, then we have our next peak, hits a minimum again, and then we have a smaller peak, etc. Now, if you have two of these patterns and you have them forming due to two closely spaced objects, well, these patterns are going to overlap. So here's one airy pattern, here's a second airy pattern. We say that the objects are just barely resolvable when this first minimum overlaps with the central maximum of the other object. And similarly, when this first minimum down here overlaps with the central maximum. This is our barely resolvable limit. If you take a look at this, you can tell that this airy pattern is from two different sources. And then once they overlap enough, basically they're unresolvable. You wouldn't be able to tell the difference between these two in terms of did this diffraction pattern come from two different sources of light, or whether it just came from a single source. Okay, the consequence of all of this is what we call Rayleigh criterion. If I asked you a question, I am drawing two tick marks on the board, or I'm drawing 2 dots on the board. And of course, you're watching this on your screen, but let's just imagine we're back in Warren Lecture Hall 2001, and I draw these 2 dots on the board, and I ask you, people sitting in the back of the room, do they see these as 2 different dots, or do they just see them as a single dot merged together? What sort of geometry and math do we need to do to determine whether you can resolve these or not? And assuming that you either have 20/20 vision, or you have corrective lenses that are appropriate for your vision, how do we figure that out? Well, Rayleigh's criterion puts conditions on this. Basically, it says that 2 objects emitting rays of light that pass through a circular hole of diameter d. So for the question I asked, this would be your retina. So the hole with diameter d are resolvable at a minimum angle of theta resolution being 1.22 lambda over d. So what do we mean by this? So let's say the hole through which that these light rays are passing are here, and let's say I have 2 objects that are separated by some distance. When, oops, sorry, let's go back to this. So when I draw a line coming from, basically a ray coming from each of these, so these are our 2 objects of interest. When I draw lines from them, this separation can be the size of the distance between the 2 objects. D specifically is the diameter of the circular aperture that these light rays pass through. Then this angle, theta res, has the following condition on the limit. Basically, when theta res is 1.22 lambda over d, this is the smallest angle you can resolve. If I bring these any closer together, given the wavelength of light I'm using to look at these, if I bring them any closer together, we're no longer going to be able to resolve between the 2 objects. So let's take a look at an example of this. So this is exactly the example that I was just talking to you about, which is, let's say that the distance to the blackboard from the back row of seats in the lecture hall is about 20 meters. So that would be, so here's a student's eye in the back row, 20 meters to the front of the board. Your pupil diameter is 3 millimeters. And so the pupil is the aperture through which these light rays pass. What is the minimum resolvable separation between between 2 green points? And specifically, if we're drawing green points, the wavelength of light corresponds to 560 nanometers. So let's apply Rayleigh's criterion, which says that theta res, the resolution limit, the theta resolution limit is 1.22 lambda divided by d. Again, this is the hole diameter, the aperture, and the hole diameter in this case is the pupil diameter. Lambda is the wavelength of light that we're using, given to us as 560 nanometers. But we're trying to figure out like what is the separation between the points that you can see, and putting a condition on this theta. Well, we need a way to relate the separation to how far you're sitting to this theta minimum. So if we take a look at this geometry back here, the separation between these 2 objects is going to be much, much, much smaller than the length to the hole or to the aperture. So we're going to go ahead and approximate this vertical length as just the arc length of this little arc here. So this arc length, which here we've called delta y, so let's go ahead and just call it delta y. Thinking back to geometry, if arc length is s, this radius is r, this is theta, you might remember that s equals r theta. Applying exactly that, our arc length is now delta y. So delta y is equal to r theta. Well, this length is approximately the same thing as the length that's, the radius, essentially what corresponds to the radius of our arc is just L. So delta y is equal to L and then times theta. And we're making the argument that this length here is pretty much the same thing as the length to, so if I were to draw a line perpendicular to the separation versus this line, these lengths are approximately the same. And once we do this calculation, you'll see exactly why we can make this approximation. So solving for theta here, we get that theta equals delta y over L. All right, so plugging that in for theta resolution, basically the smallest delta y we can resolve divided by L is equal to 1.22 lambda over d. We're trying to figure out what this delta y needs to be, so let's go ahead and isolate delta y. So we get delta y is equal to 1.22 lambda times L over d. Let's go ahead and plug in everything. 1.22. We're taking a look at green points on the board, so 560 nanometers in SI units is 560 times 10 to the minus 9 meters. The length to the board is 20 meters, all divided by the size of the aperture, which is 3 millimeters, or 3 times 10 to the minus 3 meters. All right, what do we get when we plug in these numbers? We get that this is about 4.5 millimeters, or let's just approximate it to 5 millimeters. So if I draw 2 dots on the board in green chalk and I separate them by 5 millimeters, somebody sitting 20 meters from the board in the back of the classroom should be able to just barely resolve them. If I move them closer than 5 millimeters, let's say to 4, 3, or 2 millimeters, you're likely not going to be able to resolve them anymore. Let's just go ahead and go back and talk about some approximations that we made here. So we just found for this example, our delta y is 5 millimeters, okay? This length to the person's eye was given to us as 20 meters. Let's put them in the same units. So delta y is 0.005 meters versus here to here is 20 meters. And hopefully now you can believe why I can say that this radii of my arc, or this length, is approximately the same as the length that is directly horizontal. Basically, this length here is more than 3 orders of magnitude larger. So this angle is a very, very tiny angle. So even though this is an approximation, it gives us a pretty good idea given the fact that delta y is much, much, much smaller than this L. So you never actually have to worry about whether you can make any of these approximations or not. The fact that this is really not an arc length. This is a straight distance here, but we're approximating it with the arc length, and also we're using this length here to really represent the radius of the arc that's being made. These apply at all points when working with resolution, because when working with resolution, the separation is going to be much smaller than how far away your aperture is. Okay. Next, we're going to talk about thin film interference, but before we can talk about thin film interference, we first need to remind ourselves of the index of refraction. So you might remember this from the last unit or the last quiz even, where you were given a problem and you had a light ray coming in at a certain angle, theta 1, and then that light ray either diffracted away or towards the normal, and that told us something about the speed of the wave in this medium and this medium. Let's revisit that idea. So light interacts with atoms in a material, travels at different speeds depending on what material it's in. Index of refraction, the refractive index of a material, measures how the speed of light changes compared to vacuum. So we know that in vacuum, speed of light is just c, which is 3 times 10 to the 8 meters per second. While speed of light in air is also basically 3 times 10 to the 8. So n is the ratio of the speed of light in vacuum divided by the speed of light in some medium. So this is vacuum speed of light, and this is speed of light in some medium. And examples of this medium can be water, benzene, glass. There can be different types of plastics you can shine light through. This can be all sorts of materials. You can look up index of refraction for whatever material you're working with. But the key is that the index of refraction is vacuum speed of light divided by speed of light in the medium. We know that speed of light in any medium is going to be slower than the speed of light in vacuum. So since the numerator is always larger than the denominator, we know n is always going to be greater than or equal to 1 because the numerator is always larger. And for air, it's actually equal to 1 because essentially speed of light is the same as it is in vacuum. And this is a problem we're actually going to revisit later, depending on refraction. But for now, this is our takeaway here: the fact that n is the ratio between speed of light in vacuum or speed of light in the medium. Let's take a look at this question. So if you can, go ahead and pause the video and try this problem on your own, and then I'll go ahead and go over it. So we have a red light a red laser pointer emits light with wavelength 650 nanometers in air. What will the wavelength of the beam? What will be the wavelength of the beam when it enters water? Okay, so the thing that hopefully you recall from our previous unit is going from one medium to another. So we have v equals lambda f. We already know the speed of light is going to change going from air to water. But between lambda, the wavelength, and the frequency, what's the other thing that's changing? It's going to be the wavelength that changes. Frequency is being set by the source. When you go from one medium to the next, frequency does not change. So frequency stays fixed. Between mediums, it stays the same. Okay, so we have v air equals lambda in air times f, and then we have speed of light in, what's the other medium here? In water is equal to lambda in water times f. And what we're trying to look for is what's the wavelength of the beam when it enters water. Well, we know what speed of light in air is. It's just c is equal to lambda air, which is given to us. So when they tell us that laser pointer emits light at this wavelength in air, that's basically lambda air times f. So if I go ahead and solve for f in this equation, I get f is equal to c divided by lambda air. And then I come to this equation, v water. So what I'm trying to find is lambda in water. So let's get lambda water by itself, and we get v water divided by f. And for f, I'm going to go ahead and plug in c over lambda air. So let's do that. So we get v water over c, and then since I'm dividing by lambda air, that's the same thing as multiplying by lambda air up here. Now recognize that speed of light in water divided by c is essentially 1 over n, because n is c over v in some medium. That means 1 over n is v in that medium divided by c. And that's exactly what we have. We basically have velocity of light in water divided by c. This is just 1 divided by n. So recognizing that, we get that lambda water is 1 over n water times lambda air. And 1 over n water is equal to 1 over 1.33 times lambda air is 650 nanometers. And once we divide 650 by 1.33, we'll get approximately 488 nanometers. So correct answer is C. And one of the main takeaways I'd like you to think about is the fact that when you go from one medium to the other, the two things that are changing is the speed of the wave, and the other thing that's changing is the wavelength of the wave. And how the wavelength of the wave in some medium changes, the final result that we got here was lambda water was just equal to lambda air divided by n. So if you divide by the index of refraction, you figure out what your new wavelength is going to be. Okay, keeping this in mind, let's go back to talking about thin films, but one other thing to address. We briefly talked about this before, the phase that we introduced. So let's say you have a rope and you tie it to a wall, or you basically, let's say you jam it into a wall somehow, and then you have a traveling wave pulse coming this way. When it reflects, it gets a phase of 180 degrees. So basically, the phase gets flipped at this reflection. On the other hand, if you take a rope and you tie that rope to a ring, and then you put the ring around some pole and you have a wavelength coming in that case, there is no phase introduced for the reflected wave. Well, using that same analogy and rationale, something similar happens with reflection of a light ray. So when you have an incident light wave or light ray, and we're going from low n to a higher n, pretty much where you have a slower speed of light in some medium, then we're going to have a phase introduction, so phase gets flipped. On the other hand, when we go from, so here we went from low to high, by low to high I mean from low n to high n. When you go from high index of refraction to low index of refraction, there is no phase being introduced. This is important to keep in mind when we're talking about thin film. So we did all of this introduction of, or reintroduction of this idea of refraction and then talking about defining index of refraction and phase, because we're going to use that with thin films. So let's go ahead and go to thin films. Consider a thin film of material with high N sandwiched between materials of low N. So let's talk about what do we even mean by this. So I'm going to try to draw an example of a soap bubble. So let's say this is my soap bubble. If I zoom in to, let's draw the soap bubble to be a little bit more pronounced in its thickness. So let's say here's my soap bubble. So there's a film of soap that we're looking at. Now let's just say for the soap bubble, we go ahead and zoom in further and further. Oops, sorry. And let's just go ahead and look at this section of the soap bubble. So keep zooming in till you're just looking at this boundary. So we have a film of soap, we have air up here, and we have air down here. Okay, so remember this, and this is what we're going to redraw. Okay, so here we have it. My two boundaries eventually, if you want to extend, make the bubble. This is what we're looking at. Here's my film of my soapy film. Here's air up here, here's air down here, and if you can imagine, soap bubble, okay? So we get incident light reflected. Some of the light transmits through and it gets refracted because the speed of light inside the soap film is different than air. That gets reflected from, this bottom boundary, and then it gets transmitted back out into air. You looking here, we need to determine when will these rays constructively interfere and when will they destructively interfere. Well, first we need to ask ourselves whether we pick up a phase at each of these boundaries or not. So when we go from air to film, we're basically going from low N to high N. So let's go back and check if this necessitates a phase flip. We're going from low to high N, phase gets flipped. Yes, so it does in fact necessitate a phase flip. So ray 1 gets a phase flip, or a phase of 180 degrees. All right, then we have this transmitted wave and it reflects off the bottom, and we ask ourselves, do we get a phase? Well, now we're going from high N to back to air, which is lower N. So high to low N is what this boundary here is all about. So we go look, high N to low N, no phase. So that tells us that here we pick up no additional phase. So essentially, as these two rays come out, ray 1 already has a half wavelength difference because of this phase flip. And now we need to figure out, how do we get constructive interference? All right, so let's go through and do some accounting. First, we need to look at distance traveled by ray 1 minus distance traveled by ray 2. What is that going to be? The difference between the two distances? Well, ray 1 comes in here, goes out. Ray 2 also comes in here, travels this extra distance, and comes out. So it's just this extra distance that ray 2 is traveling we need to account for. When we're doing these problems, we're assuming that the incident is nearly vertical, meaning the incident light is almost vertical, not quite vertical, but it's almost vertical. That tells us that this extra path that ray 2 is traveling is approximately just twice the thickness. Basically, we say this is about t, this is about another t, so it's about 2t is the difference. All right, so that's going to be the difference in our path length that the two rays travel along. Then we need to ask ourselves, in here, when the wave is traveling, well, its wavelength is different. So let's go ahead and write wavelength in film. And wavelength in film, as we saw not too long ago, is wavelength in air divided by the index of refraction of the film. So if you're like, hey, where did this come from? We just derived that while doing this example where we showed that wavelength inside of water was wavelength in air divided by N of water. Similarly, wavelength in some soapy water film is equal to wavelength in air divided by the index of refraction of that soapy water film. Next, let's account for all the flips. So ray 1 flips phase. So we're already off by half a wavelength because of that. So finally, to get constructive interference, we have that the path length difference needs to be a half wavelength multiple because we already have the flipping of the phase from ray 1. So we're already off by half a wavelength because of ray 1, but we need to use the rest of the difference in path to match the second half wavelength. So we summarize this as that 2t is equal to m plus a half. Usually we would just write lambda here, but we know the wavelength in the material, in the film, is different. So we're going to use wavelength of the film, which is basically wavelength of air divided by n of the film. And eventually you'll see we're going to go ahead and drop this air subscript because when we write just lambda, we assume that that's the lambda in air. So this is our condition. If going through this reasoning is not completely making sense, please come talk to me during office hours. But at the end of the day, you need to know how to use this expression. Not necessarily, you won't be asked to derive this. But there's a few different cases of this. So the case we just looked at is we went from low n to high n back to low n. But another possibility is you go from low n to medium n to high n. How do things change? So just to reiterate, the expression we just derived for constructive interference, I've rewritten here, and m starts at 0, goes up into your values. Here, t is the thickness of film, n is index of refraction, m is an integer, and lambda is the wavelength of light. And this is for low to high to low. But what if we're talking about coating on your glasses? So let's think about it. In our glasses, we have some kind of a glass lens. And then on top of the glass lens, you might have a thin coating. And that coating could be for all different purposes. Let's say it's some kind of an anti-reflective coating. That's an example. So in that case, we would be going from air to coating to glass. And in terms of index of refraction, we're going from low to medium to high. Well, when we go from low to medium, this is the higher end, so we get a phase flip. Then we go from medium, and the interface is higher here, so this reflection also gets a flip. So all in all, both of these things end up getting flipped. That means that my path length difference has to be equal to an integer multiple of lambda inside the film. So the main difference between these guys is for this case, you only get one flip of phase, meaning you need to be off by half a wavelength. Here, when both of these rays have a phase flip, that means the path length difference just needs to be a full wavelength multiple of the wavelength inside the film. Okay, if for any reason you aren't looking for constructive interference, let's say you don't want good reflection off the film, but you want bad reflection off the film, meaning destructive interference, you would just switch out this m plus a half to a m, and you would switch out this m to m plus a half. So pretty much the opposite of constructive interference. And some applications of this is anti-reflective coating. So on your glasses, we put a coating such that you actually don't get good reflection. So you would be looking for destructive interference so that you don't want light to reflect well off your glasses. So you want to put some kind of a film here that meets the opposite of this condition, basically when m gets switched to m plus a half and we get destructive interference. Let's go ahead and do just one example of thin film interference. Let's say, and before we do this example, please go ahead and pause the video and try this example yourself, because if you can work through it yourself, then you're basically good to go. Okay, we have a soap bubble. So the moment you figure out what kind of situation you have, you should draw out a picture for yourself. So just to remind you, soap bubble might look something like this. And we are zooming in far, far, far in here and looking at what happens when you have light ray come in, refract, go out, and interfere with each other. Okay, so let's draw out. We have n soap film, which is equal to 1.33. We have air out here, so n air equals 1, air out here, n air equals 1. So we're talking about the case where this formula would be valid for constructive interference. But let's see if we're looking for constructive interference. So we have a soap bubble is illuminated with white light. What color will a portion of that bubble, what color will a portion of that bubble of thickness 115 nanometers appear if viewed at an angle perpendicular to the surface? So we're talking thickness of 115 nanometers. And we want to know what color it appears. Well, if we're trying to figure out what color it appears, we're looking for which wavelength gives us constructive interference. So I'll go ahead and bring down this formula we know to be true for thin films where we're going from low, high, low. For us, air, soap, air. So that's 2T is equal to m plus a half lambda air over n film. All right, and it's the wavelength we're going to eventually solve for. So let's rearrange everything. Lambda in air is equal to 2t times n film all over m plus a half. Plugging everything in, we get 2 times the thickness is 115 nanometers, 115 times 10 to the minus 9 meters times n of the film, which is 1.33, all over m plus a half. Now, we weren't given any m, and we're just asked to see what color we see. So we'll go ahead and try a few m's and see what range wavelengths we get. All right, starting with m equals 0. And actually, before we start with m equals 0, let's go ahead and simplify this expression. So in the numerator, we have 2 times 115 times 1.3. So we get 305.9. So 305.9 times 10 to the minus 9 times 10 to the minus 9 meters all over m integer plus a half. So this basically tells us that lambda is going to be, lambda sub m is going to be about 305 or 306 nanometers divided by m plus a half. So now when we try out m equals 0, and first I'm going to make some space to work out the rest of this. Okay, so when m equals 0, we have lambda equal to 306 nanometers divided by 0 plus a half, which is just a half, and that gives us double of 306, which is about 612, so 612 nanometers. All right, that's in our visible light spectrum. It's somewhere around reddish orange. Let's try m equals 1. So theta 1 is equal to 306 nanometers divided by 1 plus a half, which is 3 halves. So that gives us 306 divided by 3 times 2, so 204 nanometers. Well, that's not going to really give us any visible wavelengths. So pretty much starting at m equals 1, we get non-visible wavelengths of light constructively interfering. So it's just m equals 0. That works. So this is the wavelength the light will see, and as we just mentioned, this is approximately around orange-red range. So that's the color you'll see where it's 115 nanometers thick. If you go to a different thickness, you'll see other corresponding colors. And this is why sometimes when you are looking at a soap bubble, you can see different colors in different parts of the bubble. All right, and that should equip you with what you need to finish off your homework.